Hi, I'm Rana Al-Utaibi. Today I'll present our work HADAD, a lightweight approach for optimizing hybrid complex analytics queries. Hybrid complex analytics queries go beyond simple SQL towards using more sophisticated ML models. These queries are basically a mix of data management tasks, including, for instance, joins, selections, and complex analytics, mostly expressed as linear algebra programs. So hybrid tasks involve both programming styles, relational algebra and linear algebra. However, some of the current systems tend to favor one or the other. Linear algebra-oriented systems treat matrix operations as first-class citizens in their programming interface, but it could be difficult to implement even simple select project join queries. Also, the expression rewrites based on equivalence that hold due to well-known linear algebra properties are not exploited in some of these systems, leading to misoptimization opportunities. In case of relational systems, not all linear algebra operations can be easily expressed in SQL. Also, achieving higher efficiency for linear algebra pipeline requires to have native support of non-relational operations. So a recent trend is to use a common programming environment where both styles can be used together, and this is being explored by a number of systems. Some of these systems extend relational database management systems with linear algebra operations via UDFs, but the semantics of linear algebra operations are hidden behind these functions. Some other systems focus heavily on physical optimizations, leaving semantic query optimization opportunities unexplored. In summary, what are the unexplored optimization opportunities in existing solutions? These systems provide no capabilities for holistic semantic query optimizations, including optimizing linear algebra pipelines based on exploiting various linear algebra properties, utilizing pre-computed results to avoid recomputing part of a given relational algebra or linear algebra computations. Such optimizations can bring enormous performance saving. Let's see some of real-world examples of the benefits of this class of optimizations. Consider the ordinary least squares regression pipeline, where D, for example, is a square matrix and Y is a vector. And suppose available materialized view, which is the inverse of matrix D. The view-based rewriting of the query is obtained by exploiting several linear algebra properties, and it is more efficient than the original pipeline since it avoids computing the inverse expensive operations. Also, it optimizes the matrix chain multiplication to minimize the intermediate result size. This leads, for example, to 7x speedup on R. An example of hybrid setting involving relational algebra operations and linear algebra operations is Morpheus system, which is a line of work that implements a powerful optimization techniques, which factorize linear algebra operation on matrix T obtained by joining tables R and S. Factorization rewrites a linear algebra operation over T into linear algebra operations over S and R tables. This technique can avoid extra storage requirements and runtime inefficiencies caused by the redundancy in the data, which is often introduced by the join. However, Morpheus system does not reason about the properties of linear algebra operations. Such reasoning together with its factorization rewrite rules can bring enormous performance saving. For example, consider the column sums operation, which sums up the elements in each column in the resulting matrix T times N and returns a vector of these sums. The direct evaluation of the pipeline, Morpheus factorize T times N by utilizing its matrix multiplication factorization rewrite rule, where the intermediate result size is a matrix of size 20 million rows and 100 columns. An alternative rewrite of the query, which is not discovered by Morpheus, is to apply the column sum on matrix T and multiply the result with N. This rewrite helps Morpheus to do better, since it enables significant reduction in the intermediate result size by enabling Morpheus to factorize column sum over matrix T. In this rewriting, the intermediate result size is a vector of size 120. This rewriting achieves 125x speedup. So our goal in this work is providing an extendable and a lightweight framework for semantic query optimizations on top of linear algebra and cross-relational and linear algebra platforms. However, the challenge in a hybrid setting is that we need to have unified reasoning about queries and views involving linear algebra and relational algebra operations, and enabling such semantics optimizations without modifying the internals of each platform. In this talk, first, I'll give an overview about our approach for providing semantic query optimizations on top of linear algebra and cross-relational and linear algebra platforms. Then we'll present our experimental results. Finally, we conclude with our contributions. Our approach overview. To find semantically equivalent optimized expression of a given hybrid expression, we propose HADAD as a lightweight framework, which takes as inputs the query, views, and properties of the data models. At the core of HADAD lies a powerful intermediate abstraction needed to reason across the data models and the operations supported by them. The intermediate abstraction is a relational model endowed with integrity constraints, which are expressive to capture the properties of the data models and the views. So opening up HADAD black box. First, the structure and the properties of these data models will be encoded relationally with the support of integrity constraints. The relational model is already captured by our internal model. In case of linear algebra, we encode the properties of linear algebra operations as integrity constraints to help reasoning about them. Then the set of views will be encoded into integrity constraints, which capture the correspondence between the views' inputs and their outputs. The hybrid expression will be encoded into a relational query. Our encoding approach is centered around conjunctive query. Now the problem has been reduced into a purely relational setting. Our rewriting engine of choice is the relational rewriter under integrity constraints. We have integrated into that engine two different cost models to prune out inefficient rewritings at early stages of rewriting candidate search phase. The minimum cost relational rewriting is then decoded into a platform-supported query language. Our reduction guarantees that the found minimum cost rewriting is an equivalent to the original query under a set of integrity constraints. In the rest of the talk, I will mainly focus on the reduction from linear algebra language and model into the relational model with integrity constraints, so we can reason about queries and views involving linear algebra pipelines. The relational model is already captured by our internal model. So we represent the matrix model and linear algebra operations using a set of virtual relations. We call them virtual relational encoding of matrix. For example, we have a name relation. The name relation attaches a unique ID to each matrix identified by a name in. And we have the size relation, which captures the dimensionality of the matrix. Also, for example, matrix multiplication operator would be modeled as a multiplication relation with intending meaning that the resulting matrix IDR is equal to IDM times IDN. Other operations, such as addition, transpose, and inverse, for example, are encoded in the same fashion. We note that these are not IDs of individual matrices objects. These are IDs of equivalence classes of expression induced by value equality. Two linear algebra expressions are assigned the same ID if and only if they are in the same equivalence class, meaning if and only if they are value equal. For example, because of associativity of matrix multiplication, the two linear algebra expressions that you see here, even though they are syntactically different, they yield the same result. HADAD, as it reasons about these expressions with the knowledge about the associative property, it will end up concluding that these expressions are equal and assigns them an equal ID. We currently support a wide range of linear algebra operations, which are common in real-world ML algorithms, including matrix operations, matrix vector or scalar operations, as well as various matrix decompositions. So in order to capture the properties of these operations and make the relations that model these operations behave according to their intended meaning, we have to restrict what can be in these relations rows, and we do so by introducing integrity constraints. For example, the constraints for name relation states that two matrices with the same name have the same equivalence class ID. The constraint is expressed in first-order logic. For example, here we have two different matrices IDs, M and N, and both have the same name N. This implies that they are equal. The constraints of the size relation states that matrices with the same equivalence class ID have the same size. For multiplication relation, the constraint states that the relation is functional, meaning products of pairwise equal matrices are equal. Also, we capture the properties of linear algebra operations as integrity constraints, so we can reason about them. The constraint we have here captures the associative property of matrix multiplication. This constraint captures the fact that the matrix transposition is distributive with respect to addition. Other linear algebra operations properties will be encoded in the same fashion. The extended version of the paper details our encoding. Now, the relational encoding for queries and views. So the encoding relations that we've just presented are virtual, meaning we only use them to encode linear algebra queries and views relationally to reason about them. For example, we have here an R program where in the first part, we load M and N matrices. Then in the second part here, we compute the inverse of M, then add the result with N matrix, and finally compute the transpose. We encode the expression as a conjunctive query, where the scan operation, for example, in the first part, is encoded as a name relation, and the information about the dimensionality of the matrix is encoded as a size relation. As for the linear algebra expression part, we encode the inverse of matrix M using the inverse relation, then we encode the addition with matrix N using the add relation, and finally, the transpose is encoded using the transpose relation. As for each of you definition defined in linear algebra program, it will be translated into a relational constraint. The constraint shows how the view's inputs are related to its outputs over the encoding relation schema. Now, the relational rewriting engine will select an efficient rewriting based on a cost function. The cost function estimates the cost of an expression E as the sum of the intermediate result sizes if one evaluates E as stated, meaning if it's evaluated in the syntactic order dedicated by the expression. Real-world matrices may be dense or sparse. For sparse matrices, several systems and libraries have economical representation that don't store zeros, which our intermediate result size excludes. To estimate the number of non-zeros, we've incorporated two different sparsity-aware estimators, naive metadata estimator and matrix and MNC estimator. Due to time constraint, we refer the audience to the paper for more details about these sparsity estimators and how we integrate them and use them in our rewriting engine. Now, the decoding of the rewriting. The found minimum cost rewriting will be decoded into the platform-supported query language. For example, the name and size relations for matrix M and N will be decoded back into matrices loading statements expressed in R. And the combination of transpose, add, and inverse relations will be decoded back into the corresponding R linear algebra expression. Let's see an end-to-end example of our reduction. We have expression E, which can be fully rewritten using the view V. The expression is encoded as a conjunctive query using the virtual relational encoding relations, and the view is encoded as an integrity constraint. The set of linear algebra properties are encoded as a set of integrity constraints. Now, the rewriting engine will prune out inefficient rewritings based on a cost model. Finally, the minimum cost rewriting is decoded to an expression expressed in linear algebra language, which is equivalent to the original expression. Our experimental evaluation. We have evaluated our approach in two different settings. First, on top of linear algebra-oriented systems, and second, on hybrid systems. In this experiment, we are going to present subset of our results. The extensive set of experiments are detailed in the paper and its extended version. We evaluated our approach on top of R, NumPy, SystemML, SparkMLib, and TensorFlow. We selected 57 linear algebra pipelines used in previous studies or frequently occurring in real-world linear algebra computations. As for the datasets, we use real-world sparse matrices and synthetically generated dense matrices. In this experiment, HADAD improved the performance of linear algebra pipelines in absence of views by just exploiting and reasoning about linear algebra properties. Popular linear algebra-oriented existing libraries or systems which don't fully reason about linear algebra properties missed most of the efficient rewrites. We show here the distribution of the rewriting speedup on R. For clarity, we split the distribution into two figures. On the left, 25 pipelines out of 38 pipelines with a speedup lower than 10x. On the right, the remaining 13 pipelines with a speedup up to 57x. As for the linear algebra view space rewritings, we have defined a set of 12 views that pre-compute the result of expensive linear algebra operations. These views can be used to answer 30 pipelines from the workload and can be discovered by exploiting several linear algebra properties. The minimum speedup achieved by utilizing the views is 2.5x, and the maximum one is 150x. For example, consider here one of these pipelines. We have here the matrix chain multiplication pipeline, and the view V1 can be only discovered by exploiting the associative property of matrix multiplication. Existing linear algebra-oriented systems don't exploit the knowledge of views. In this experiment, we evaluated our approach on top of Morphus, which is a cross-relational linear algebra platform for factorizing linear algebra operations. Also, we've designed hybrid micro-benchmark or real-world Twitter datasets and evaluated it on top of Spark and SystemML. We discuss subset of our results and refer the audience to the paper for the rest of the experiments. In this experiment, we studied the performance benefits that HADAD can bring to Morphus. We evaluated a set of 8 pipelines on Morphus R and their rewritings found by HADAD. For these pipelines, their efficient rewrites that are found by HADAD are missed by Morphus. The minimum speedup achieved by HADAD is 1.3x, and the maximum one is 125x. As an example of one of these pipelines, we have here this pipeline, which computes the addition of two matrices, T and N, and sums up the cells values of the resulting matrix. Matrix T obtained by joining tables R and S. Morphus runs the pipeline as is, since it doesn't factorize element-wise operations. However, HADAD distributes the sum over the addition. This rewrite avoids large and dense intermediate result of the element-wise matrix addition and enables Morphus now to factorize the sum operation over matrix T to operate over R and S tables instead. The rewriting of this pipeline achieves 20x speedup. For this experiment, we create a hybrid micro-benchmark of 10 queries on real live Twitter datasets. Queries consist of two parts, relational algebra pre-processing part and linear algebra analysis part. For each query in the benchmark, HADAD applies several optimizations, including views-based rewriting of the pre-processing part, selection pushdown from the pre-processing part into the analysis part, and cross-relational and linear algebra view-based rewriting, and finally, linear algebra properties-based rewriting. The minimum speedup achieved by HADAD is 2.3x, and the maximum one is 16.5x. HADAD captures these optimizations because it reduces all rewrites into a single setting in which they can interact, relational rewrite under integrity constraints. To conclude, HADAD finds rewrites that existing system missed because it exploits the knowledge of views and the data model's properties, which leads to significant performance gains. HADAD brings semantic query optimizations on top of linear algebra and cross-relational and linear algebra platforms with no modification to their internals. HADAD enables these optimizations based on a powerful intermediate abstraction of a relational model with integrity constraints. Thank you.